Hello, everyone. Hello, Steven.
Good morning.
I'm Daniel Rodan-Legrain, Quantum Science and Engineering Lead for North America here at Qblocks, the sponsor of today's session. This fireside chat brings together leading voices shaping the quantum ecosystem, from theory to hardware to national initiatives. So we've briefly hosted Will Oliver, Bert de Jong, and Peter Shor. And today it is a true honor to welcome someone whose theoretical work has pretty much defined how we build and think about superconducting quantum computers, Professor Steve Girvin. So Steven is the Sterling Professor of Physics and Applied Physics at Yale, a member of both the US National Academy of Science and the Royal Swedish Academy of Science, and you are a co-founder of Circuit QED, the theoretical backbone of superconducting qubit systems. So Steve's career spans from fractional quantum Hall effect to quantum error correction, and his collaborations with Michel Devoret and Rob Shokov have pretty much inspired an entire generation of quantum hardware research, including myself. So maybe on a personal note, your career is actually really inspiring, Steven, because I also moved from condensed matter physics to quantum computing during my time at MIT, though certainly at a much more modest scale. And of course, this year's Nobel Prize in Physics, recognized to your longtime collaborator, Michel Devoret, for pioneering work in quantum engineering. Maybe a recognition that I could say few people are better positioned than you to reflect on, both scientifically and personally. So, Steven, it's really a privilege to have you with us today. And to everyone watching on YouTube, please feel free to post your questions in the chat, and I will bring a few towards the end. So let's maybe, start where it all began, the origins of Circuit QED. So your career really started in condensed matter physics, even long before superconducting qubits entered into the picture. So, Steve, what drew you from studying collective electron behavior to exploring quantum circuits and quantum information?
Well, it's a kind of an interesting story involving sort of random forks in the road. I was, as you say, a condensed matter theorist. John Hopfield's last condensed matter student before he became a neuroscientist and so forth. And I spent a long time studying the fractional quantum Hall effect. And I did a little bit of work on mesoscopic superconductors and things not exactly like microscopic quantum tunneling, which was recognized with this year's Nobel Prize, but similar idea, looking both at normal and superconducting junctions and how they interacted with the electromagnetic environment. But I didn't know that there were, in the 1990s, a few crazy people looking way ahead and dreaming about quantum computers. I'd never heard of quantum computers, didn't know anything about quantum information. And in 1999, Yasunobu Nakamura, who was then at NEC, did his famous experiment with Rabi flopping a Cooper pair box, which was sort of the first time dynamics experiment with effectively a superconducting qubit. And I happened to see that paper when it was published in Nature, and I was completely just stunned and found out about this whole field that people were trying to build. And that paper had a dramatic influence on me and more or less began my rapid turn from traditional condensed matter theory to starting to think about quantum information and superconducting qubits. And then in 2000, around 2000, I met Rob Scholkoff, uh, and in 2001, I moved to Yale. Michelle moved 6 months later in January of 2002. And the, the real sort of defining moment for me was when I visited Yale to give a colloquium on fractional quantum Hall effect, and Rob Scholkoff was on my schedule, and we had this incredible 45-minute conversation at his blackboard in his office, and he had invented the radio frequency single electron transistor, which was sort of the world's fastest counter of the smallest beans, as I like to say. So he could detect a tiny fraction of an electron charge in microseconds, with tens of megahertz bandwidth. And he wanted to use that to measure, and was using that to measure the charge state of a charged qubit, the Cooper pair box. And he had also taken, I didn't know almost anything about cavity QED. I kind of knew there were, mirrors and cavities, and it changed, you could put atoms inside and do something. But he had actually taken Jeff Kimball's course at Caltech on open quantum systems, and knew a bit about cavity QED. And he wanted to put a Cooper pair box inside a microwave resonator and measure the state of the qubit as it interacted with photons using his RF single electron transistor. And without completely understanding what I was saying, I said, well, why don't you do it, like in cavity QED, where you measure the state of the photons coming out rather than, the charge state of the qubit. And that turned out to be, a useful suggestion after a couple years of understanding what it really meant. And, the sort of interesting thing is that Rob was a radio astronomer. I mean, he built very sensitive mixers and amplifiers for detecting microwaves and radio telescopes. And I was, when I was a teenager, I was a ham radio operator and strung antennas between trees and had a shortwave transmitter and learned about matching impedances and things, by actually turning knobs myself. And so even though I'm a theorist, that sort of amateur experimental background turned out to be extremely useful for understanding the quantum mechanics of electrical circuits. So that's sort of how we got started. And then, it was a pretty big change for me. I didn't know really anything about quantum optics, coherence, open quantum systems. So I had to take a couple of years and learn all that stuff while we were starting to think about what experiments could we do and how should we do them. But it was so it was a big change of direction, but it was very kind of refreshing and exciting to change directions in that way. Pretty far into my career.
What a story. And what made you and Rob and Michelle realize that this could actually be a powerful scalable architecture for quantum computing?
Well, I think at first it was really, we were aware that it could be an architecture for quantum computing, but at first it was really basic physics. How do you apply the ideas from quantum optics to quantum mechanical superconducting microwave circuits. And there was a lot of just borrowing of ideas that had been developed in cavity QED with optics, but in a completely new and much stronger coupling regime where you could have even a single atom can produce enormous nonlinearities with a small number of photons, whereas in solids, the nonlinearities aren't very strong and so forth. So there was a lot of just focus on fundamental nonlinear quantum optics in a completely new regime. But, and of course we knew it could be interesting as a computing architecture, but that feeling got stronger only after things really started to work, and we made progress in controlling individual qubits and individual microwave photons. So it gradually evolved towards a more applied direction over the years as things got better and better and worked better and better.
And now we wouldn't be where we are without all of those discoveries, Steven.
Yeah, it's kind of amazing to me that, most of the stuff I worked on in, fractional quantum Hall effect and so forth, very beautiful fundamental physics, fractional statistics and fractional charges and all kinds of exciting stuff, but not really any conceivable practical applications. And the fact that this has become sufficiently practical that people are investing serious money in engineering it and scaling it up is still kind of unexpected for me and pretty exciting.
So from foundations to recognition, let's talk about that, and in particular, let's talk about Michel Devoré and this year's Nobel Prize. So Michel Devoré was your longtime collaborator.
Yes.
And he was awarded the Nobel Prize this year.
Right. Yeah, it was extremely exciting for us, and it was clear for many years that he had an excellent shot at winning a Nobel Prize. It wasn't clear for which of his many discoveries it would be that he would be recognized. But and it's interesting that this was actually work from the very beginning of his career when he was a postdoc in John Clark's lab at Berkeley, and John Martinez was actually a grad student in the same lab. So it was from the about 40 years ago in the mid 1980s, and the significance, I would say, of that work is the following. So Tony Leggett, who had interesting ideas about, foundations of quantum mechanics, and could quantum mechanics fail to work at macroscopic scales, and maybe there's some term in the theory that we've left out that causes natural collapse of superpositions and makes things look classical at large scales. And so he had proposed that certain superconducting circuits could behave in a macroscopic way quantum mechanically. That's a little confusing concept, actually, because superconductivity is very quantum mechanical, right? You have a pairing of spin up and spin down electrons with opposite momenta, and they have all kinds of quantum coherence and superpositions of a pair being in a certain momentum state and not being there. And why isn't a superconductor extremely quantum mechanical. Well, it is in some sense, but in another sense, it's very classical. It has all of the pairs of electrons are condensing into the same macroscopic quantum wave function that has some particular phase. And that phase actually behaves rather classically. People figured out that if you have a Josephson junction, Josephson figured out that the current that flows through the junction was proportional to the sign of the SIN sign of the phase difference across the junction, and that the time rate of change of that phase corresponded to the voltage. But then people wrote down sort of a Newton's law, a classical equation of motion for the phase. And it described the behavior of superconducting circuits extremely well. There's resistance causes sort of, you can think of the phase as kind of the position of a particle, not a real particle, but just it's a number, and it's simplest to interpret it as the position of a particle. And that particle moved around in some potential, and it had some friction associated, because when it moved, the phase changed. That means there's a voltage. When there's a voltage and there's a resistor, you have dissipation. So it just looked like a classical particle with some friction. But Tony Leggett had the idea that actually that classical particle could itself behave quantum mechanically if we built a circuit where there was not too much dissipation. And so the Clark lab decided to set out to do an experiment to try to prove that the superconducting phase could be viewed as the position of a quantum mechanical particle, not a classical particle. And they did two experiments which were recognized, by the Nobel Committee. The first was to arrange the potential energy so that the particle was trapped in a little potential well, but occasionally would tunnel out through a barrier and start rolling downhill. The potential was on a slope. And that once it starts moving downhill, it's changing with time, its position. So that corresponds to a voltage. So it's sitting there, there's a supercurrent flowing in the circuit, no voltage, and then randomly at some moment, just like radioactive decay, the phase particle began to tunnel through the barrier and move. And so you would see that experimentally as suddenly a voltage would appear. And of course, there are many things that could make that happen. Temperature, noise. They had to do heroic filtering and cooling and making sure the electrons were as cold as the actual refrigerator temperature. Many, many heroic steps and many serious control experiments to make sure that what they were seeing was actually quantum mechanical tunneling of this phase particle, and not, temperature or some noise from room temperature disturbing it and making it move. Then the second experiment was to do spectroscopy by shining microwaves on this thing and see the particle move from one quantized energy level to another. And they saw that because once it moved to a higher level, it was easier to tunnel and out. And so they proved two fundamentally quantum things were happening: tunneling and quantized energy levels. And of course, quantized energy levels tells you now have a kind of synthetic atom, which today we call a qubit. It wasn't called that, of course, at the time. But this was really the historic beginning of that laid the groundwork for all the subsequent developments in superconducting quantum circuits. So very appropriately recognized, I would say, by the Nobel Committee.
And such an elegant experiment
Yeah,
as
I
well.
mean, and very difficult. Other groups, Bell Labs and IBM, had tried to see these things and didn't, partially or not at all succeeded. And they had to invent copper powder filters, and they had to, you know, the John Clark lab was, John Clark was Mr. Squid. I mean, they were doing all these things with superconducting circuits and dealing with getting the noise levels down, way down. So that, they were perfectly positioned to do these experiments, assuming you had a spectacularly good postdoc and graduate student, which he did.
Amazing. So you worked for a long time with Michel.
Yeah.
How would you describe the dynamic between, let's say, your theoretical approach and his experimental intuition? And I was actually curious if there were moments where theory and experiment kind of pushed each other in unexpected ways.
Yes, it was very interesting. I mean, Michel and I, well, first I should say Michel's actually a pretty good theorist, which is annoying for for some of us. And he actually scooped me on a paper in the 1990s, not unrelated to this macroscopic quantum tunneling stuff. So we both managed to publish in Fitzgerald Letters, but he was several months ahead of me, which was very annoying. But, it's very interesting to have him as a colleague. He has a unusual intuition. I mean, he has pictures of how things work. Sometimes they don't seem so simple or so obvious when he first explains the picture to you. But that's extremely useful, for a theorist, because theorists do all these complicated things, and experimentalists say, well, it's sort of like this, and it sort of clarifies your thinking because their picture is so much simpler and often perfectly accurate. But I would say we had many, many very productive arguments about what's going on and what the results of some proposed experiment would be. And that was a lot of fun. So in particular, his postdoc, Michael Hatridge, did this famous experiment on determining the back action of a weak measurement on a qubit. So you're in some superposition state and you're trying to measure whether it's 0 or 1. And if it's a very weak measurement, you get a tiny signal but a lot of shot noise, then the state changes, but it's not the kind of sudden projective collapse that you are taught about in when you first learn the Copenhagen interpretation of quantum mechanics. It's a very gradual change in the state of the qubit, which they were able to measure in a different way, and that's called the back action. And Michel and I had a long series of arguments about if you measured both, we do the measurement by shining microwaves on a cavity containing the qubit, and there are different measurements you could make. You can make a homodyne measurement, one of the quadrature amplitudes of the microwaves. Or you can make a heterodyne measurement where you measure both sort of the cosine omega t oscillations of the electric field and the sine omega t. But in quantum optics, you recognize that's like measuring the position and the momentum simultaneously of an oscillator. And they don't commute. They're incompatible observables, so you can't measure them perfectly. And that was the experiment Michael was doing. And Michelle and I had long series of arguments about what did that mean if you were trying to measure these two incompatible things? Was it going to produce decoherence, or was it going to just produce something else, some other kind of back action? And we each managed to change the other person's mind, at least twice. And we went back and forth, back and forth. And we finally got the intuition right just before the experiment started working. And that was, even quantum mechanics is sufficiently weird that even people with decades of experience can get confused and uncertain what the answer is. And those kinds of conversations are where you finally, you confuse each other and then you finally get it right. Those are just very, very fun and fruitful and fulfilling. And, I had many conversations like that with Michelle, but that's the one that I remember best.
What an exciting environment to be in, actually. And in general, being
it was quite unusual. Rob, there were no walls between Rob and Michelle's labs, and and we had a joint theory experiment group meeting every week, which started out with 4 people in a little alcove in the lab in a hallway, and then today there's a whole dedicated room and 50 people show up. We outgrew that original space, but it was pretty unusual to have such tight coupling between 2 experimentalists and with theorists who joined the effort. And there's the hardware is still, with all the progress we've made, right? There are lots of problems at the hardware level with finite lifetimes and all these things. And while it's important for there to be theorists who are thinking ahead to the future when we have fault-tolerant hardware. Right now, at least for people like me who are closely connected with experiment, it's important to have some real-world understanding of, just how bad some of the hardware problems are, so that, you can help change the qubit design, or figure out what we call microwave hygiene. That was one of the big problems was this is microwave electronics in a very unusual regime where the only impedances allowed are 0 or infinity. Everything else produces dissipation. And it turns out, there are all kinds of ways for microwaves to leak away from places that you thought were hermetically sealed. And there are just lots of practical things that theorists and experimentalists need to collaborate on to get the coherence times to have gone up by about a factor of 1,000,000 since Nakamura's first experiment. And, that was hard work. But
let's talk about that, Steve. Let's talk about Yale and the present challenges of scaling and fault tolerance. So Yale's group, yours, Rob's, you have been leaders in bosonic codes, in cat qubits, and break-even quantum error correction. So could you walk us a little bit about what excites you most about these developments and how they connect to this longer vision that you're mentioning of fault tolerant quantum computing?
Sure. So it turns out that quantum error correction is, it's the grand challenge, and it's really, really hard. You have the hardware making errors. Your qubits are falling from the excited state to the ground state, or microwave resonators are losing photons, or there's dephasing. And furthermore, the circuits that you have to build to correct the errors are made of the same components, and so they too make errors. And the real goal is what we call fault tolerance, which is, roughly speaking, the ability to correct errors even when the error correction circuit itself is making errors. And that's the fact that that's possible theoretically is amazing, and it's beginning now to happen in practice. And it's happening both with superconducting traditional qubits like transmon qubits, and it's also happening with these bosonic codes that form qubits out of superpositions of microwave photon states in resonators. We like the latter a bit because oscillators have a bigger Hilbert space than a qubit. You can build in some redundancy and get an error correcting code just inside a single resonator without having to, typical qubit error correcting code takes many physical qubits, entangles them in some clever way to produce the logical qubit. And but ultimately, bosonic codes will give you some error correction gain. They will, you can build an error correcting code inside them, and the lifetime of that logical qubit will be longer than the best physical component it's made of. But in the end, you're not going to get error correction gains of millions or billions. You're going to get, a few, maybe 10 someday. Right. And so you're going to need to then take many of those bosonic codes and put them together into a surface code or a color code or some other traditional qubit-like error correcting code to get the the dramatic increases in qubit lifetimes that we need. Right now, I would say, so Michel's experiment there was a cat code experiment with Rob that was the first one to break even. Michel's GKP bosonic error correction experiment had an error correction gain of about a little under 2.5, I think. And the recent experiments at Google have achieved about the same gain using hundreds of physical qubits instead of one single resonator. But the actual wall clock lifetime of Michel's GKP logical qubit is still twice as big as that Google one. So they're kind of comparable in results, but very different in hardware cost. Now, as people figure out how to drive down the physical error rate, Google will be able to achieve very big error correction gains, hopefully, from their large surface codes. So we have to work at many levels. We have to make the qubits better. The lower the physical error rate, the easier it is to correct the errors. We have to make better error correcting codes. We have to have better high-speed control electronics, as your company works on, to do measurements of the errors and then correct them. And then higher up in the software stack, maybe you need to co-design your algorithms for the particular types of errors that are left over. There's room for improving the full stack at every level. And we still have, a long way to go. Error correction is just now making things slightly better. it's pretty interesting to compare cold atoms like Rydberg arrays to superconducting qubits. So when we talk about error correction gain for memory, we say you have a collection of physical qubits. Among those, there's a very best one. And then when you put them together to make a logical qubit, you want to beat the lifetime of that very best component. That's what if your logical qubit lives twice as long, we call that an error correction gain of 2. That's for memory. For atoms, they're so coherent, they have 1 second coherence times, they'll probably have a hard time getting error correction gain for memory. But the reason the atoms are so coherent is because they don't couple to things very well, in particular to your control system. And so it's hard for them to do high fidelity gates. So they need error correction for gates, whereas we need error correction for memory, essentially, because our gates are fast and pretty high fidelity. So we're both struggling with error correction, but it's a slightly different thing.
Indeed. So I would actually like to follow up on something you mentioned about co-design and eventually large-scale collaboration.
Yeah.
And in particular, you've led, large multidisciplinary effort. The Yale's Quantum Institute, the Co-Design Center for Quantum Advantage.
Yeah.
So, this collaboration between academia, industry, and government seems to be, I would say, more pivotal than ever. So, from your experience, Steve, what's the unique advantage of national centers and joint programs? And let me also ask you, how can smaller university labs continue to have an impact as the field industrializes?
Yeah, I think this is a very, very important question. In the history of CMOS, of course, there were, hundreds of billions, probably trillions of dollars invested as that technology matured. But there was still academic research for decades after it became a massive industrial thing. And I think there's a close analogy here. If you're IBM or Google or a large company that's trying to focus on scaling up, you have to kind of pick your hardware architecture and stick with it. If when you're investing $1 billion in scaling up a particular architecture, you don't want somebody distracting you with, "Hey, I have a better way to do it that might work, but I'm not sure." Okay, and whereas academic labs that's a perfect PhD project, right? To say, "Oh, maybe there's a better way to do this. If I prove it doesn't work, that's a fine PhD. If it happens to work, then that PhD
That's an amazing PhD.
can bring those ideas to the company that they join, and so it's kind of de-risking the exploration for completely new ways to do things that industry, whether you're large or small, it's too risky to do. And it worked that way in CMOS also. I mean, the high dielectric constant materials that were eventually introduced as they were needed to be introduced, they were developed in academia. So I think there's plenty of, even though we are now industrializing, industry recognizes that it's critically important to have fundamental research, both for, coming up with new ideas, and the sort of miraculous feature of how we do this kind of research in the US is it's simultaneously training the workforce to work at the frontiers of knowledge through graduate students and postdocs. So I think that both academia and industry need each other and will continue to, it'll be a long time before quantum computers are commodity products that are not the subject of fundamental research in universities, I would say.
I'm glad you bring this up, because every single speaker we've been discussing with brings up the importance of workforce development
Yeah.
and training the next generation of scientists beyond even just pure physics.
Right. Yeah. I was on this NSF panel that tried to sit down and think about how to create an undergraduate quantum engineering program. What kind of courses would you need and so forth. It's an interesting topic. Like right now, most quantum computers are assembled by physics PhDs or PhD students by hand, and it's become more professionalized in large companies, but still, they're not being mass produced, and we need to develop a workforce in such a way that people who have you should not need 6 years of graduate training in quantum physics to be able to contribute. And so how do you do that? You don't have to take even a physics course in quantum theory. There's a basic. Like I teach an undergraduate course in quantum computing and information, where I do not do the Schrodinger equation or time dynamics or waves or anything. It's just quantum mechanics as linear algebra. Here's the rules. And we need computer scientists, mechanical engineers, chemists, physicists at the bachelor and master and PhD level to build out a robust workforce that can, there's so many challenges that we have to meet. And in particular, PhD physicists are not generally systems engineers or systems integrators. So we have a lot to learn from computer scientists on that topic. And no one person can know all of these things, can understand every detail at every level of the stack. So, this comes to co-design. We need it's very, very important to have abstractions. You're the expert at, maybe the hardware level, but you have to simplify the story as you pass it up to the transpiler designer or the compiler designer. And you have to simplify it, but it still has to convey the key information. What is the noise model, the error model? How long do gates take? The sort of resource requirements. But you can't overwhelm them with all the dirty details of of the physics that fascinate you. And it's very important to have very good abstractions as you move up the stack, so that all these different people, different communities can talk to and understand something about the layer below them and the layer above them in order to make progress. So it's not something that typical physics labs have experience with. And so that was one of the things in this large DOE center that for which I was the founding director, Co-Design Center for Quantum Advantage in Brookhaven. We learned, one of the things I liked about it was that suddenly there were all kinds of new people at different institutions that I was talking to. So I began to talk for the first time to computer scientists and develop close collaborations with Nathan Wiebe at Toronto, for example, and Rob Sholkoff and Michelle started collaborating with Andrew Houck and Natalie DeLeon at Princeton on material. We had never thought about materials science before. We didn't need to, because microwave hygiene and other basic simple things, filtering, were limiting us for 15 years. But now that those problems have been solved, we have to start thinking about material science and what can we get rid of to make the lifetime longer and so forth. So it's been very, very productive from that point of view.
Amazing. So Steve, maybe one more question before we close and we jump to the YouTube chat questions.
Sure.
Let's take a look at the future of quantum science and technology, and maybe a more personal note from your end. What would you say gives you the most optimism about the next decade of quantum research? Is it like a specific technology? Is it a theoretical direction? Or maybe, the next generation entering the field?
Well, I continue to be amazed by the rate of progress that the whole field is making, and there are many platforms that are extremely interesting: superconducting qubits, trapped ions, Rydberg arrays, some others which maybe are not quite as far along, but you never know. They could suddenly, some young person could suddenly come up with a new technology that's even better. So the rate of progress is enormous, but I have no idea, honestly, if there'll be a fundamental showstopper that appears, or will we be able to extrapolate the current amazing rate of progress forward for more and more orders of magnitude of improvement? And I honestly don't know, but you have to be optimistic based on extrapolating from the past, how far we've come. Much further in 20 years than I would have guessed, I have to say. But
it's been impressive.
Yeah, and it's very important that people working on, we're all struggling with the same problems, different aspects. Ion traps have their problems, Rydberg atoms have their problems, superconducting qubits have their problems, but we're all can borrow ideas from each other about how to deal with certain types of decoherence or invent clever new gates and so forth. It's very, very important that we continue to learn from each other, even though the technology platforms are very, very different, but we're all trying to do the same thing. So I think that's one of the delights of the field, that I can talk to atomic physicists and sort of pretend I'm a pseudo-atomic physicist with synthetic atoms and talk to computer scientists and so forth. So the grand challenge, as I said, is getting out of the NISQ era into the era of fault tolerance. It's not, Rob Sholkoff likes to say, it's not like one day suddenly you're fault tolerant. It's a journey, and you're just making things more and more tolerant of more and more kinds of faults. And it's a very gradual, it's a journey, not a destination. And I think we're beginning to make some progress as we, right now we're just beginning to get error correction to work, but we're starting to learn a little bit about fault tolerance. And that if we continue to make progress there, then I think this whole thing is going to succeed in really, really getting us out of the NISQ era.
Sounds great. Steve, we have time for maybe one question from the audience.
Sure.
What advice would you give to someone considering entering the quantum field, whether that be a student, a professional looking to transition, or let's say an entrepreneur?
Well, I do get this question quite often, and I'm not sure I have the perfect answer. But let me say from the point of view of being a graduate student. So when I was a beginning graduate student, I had no sense of perspective on what are the big questions, why are they important, is this particular little problem that I could spend time working on worth working on, or what should I be? How should I be spending my time? But John Hopfield was influential in the sense that uh, he had a very broad view, and he would be willing to borrow ideas from completely different subfields in order to solve a problem. And so just learning, and it's very hard, it takes experience, but learning to get some sense of perspective on you've made a deep dive as in your thesis on some particular thing. But while you're doing that, just keep looking around you for ideas you can steal and use. There's only so many good ideas, and the atomic physicists come up with some, we come up with some, etc. And just try to build up a sense of perspective, because there are only so many hours in the day, and you should spend your time working on the thing that's important and yet probably soluble. There are some things that are important that we have no idea how to solve, and there are some things that have a chance of being solved in the near term. So learning how to do that is I think, very important. It's amazing to me how much, entrepreneurs often know very little actually about how the technology works. And unfortunately, that's fine, I guess. They have business expertise. But there's also a very large amount of hype in our field now, which I'm worried about. And, that connected with a large amount of money flowing is potentially bad for the field. So I think it's incumbent on everybody to at least learn something about the basic physics of what's possible with this kind of technology, because it's not going to solve all possible computational problems.
Do you have any resource you would recommend for people to read about that?
Well, there really, I don't actually. There are some of the big consulting companies like Deloitte have put out fairly responsible primers for CEOs. So if you're in that category, some of those are pretty good. Some of them are terrible. They're just falling victim to the hype. But there are a few good ones. And then for students, there are various review articles. Let's say if you're interested in Circuit QED, my Les lecture notes, or Will Oliver's review article on basically quantum engineering approach to superconducting qubits. There's some few good resources out there.
Both of them fantastic. I know them firsthand. Well, Steve, I think we're reaching the end of this conversation. Thank you so much for your time and all the insights with us today.
It's been a real pleasure. It's a fun subject.
It is, and we could probably spend several more hours discussing about that. For every explanation you give, if I have even more questions to ask you, Steve. But let me say that your work together with Michelle's and Rob's has really laid the foundation for what we now take as granted in superconducting quantum computing. And at Qblocks, our motto is building quantum together. And I think today's conversation has been a perfect reminder of how collaboration between theorists, experimentalists, and engineers drives progress.
Yes.
So as a small token of appreciation, Steve, we've sent you one of our Qblocks mugs to your Yale office. And hopefully it's going to be a good companion for your next round of theory experimental discussions at Yale.
Great. Thank you very much. I look forward to receiving it.
And for everyone watching, the recording will be available at the Qblocks YouTube channel, also on Apple Podcast and Spotify under the podcast name Quantum Builders. So please stay tuned for upcoming fireside chats. We have other exciting speakers ahead. And Steve, one more time, thank you again for this very inspiring conversation.
Thank you very much. It was fun.